So this is the second part of VAE, that is variational autoencoder. So variational inference formulation. The formulation of variational inference in a VAE is as follows. Approximate posterior distribution. We have an approximation of the posterior distribution. The true posterior distribution is, we have the true posterior distribution. So the aim is to find a similar distribution that approximates the true distribution of probability of Z public X as closely as possible using the KL divergence method. Now KL variance equation compares two probability distribution, that is Q Z by X and P Z by X, to measure the differences. During VAE training, we try to minimize the KL divergence by increasing the evidence of lower boundary, that is ELBO, a combination of the reconstruction term and the KL divergence. The reconstruction term assesses the model's ability to reconstruct input data, while the KL divergence measures the difference between the approximate and actual distribution. Neural networks of the model. Neural networks are commonly used to implement VAEs where both the encoder and decoder components are implemented as neural networks. During the training process, the VAE adjusts the parameters of the encoder and decoder network to be minimized two key components, the reconstruction error and the KL divergence between the variational distribution and the true posterior distribution. This optimization task is often accomplished using techniques like stochastic gradient descent or other suitable optimization algorithm. Variational autoencoder execution. Before getting into configuration of the variational autoencoder, it is critical first to understand the fundamental concepts. While VAE implementation can be intricate, we can simplify learning by following a logical and coherent structure. Our approach will involve gradually introducing the fundamental concepts and progressively delving into implementation details. We will adopt a hands-on approach to enhance comprehension and provide illustrative examples throughout the learning journey. Data preparation. The provided code includes leading the MNST. MNST is the data set, a widely utilized data set for machine learning and computer vision tasks. This data set comprises 60,000 grayscale images of handwritten digits from 0 to 9, each with a size of pixel 28 by 28, along with the corresponding labels indicating the digit represented in each image. This allows us to link the images with their respective categories or names. To prepare the input data for training, the code applies normalization by dividing all pixel values by 255. Furthermore, we reshape the input data to incorporate a batch dimension. The pre-processing step ensures that you format the data properly for model training. Now this is the kind of code that can be used, which is very simple, but then one has to understand it. So import TensorFlow as TF, import NumPy as NP, then this is the condition that you have to apply, that is xtrain, ytrain, xtest, ytest, and if TF, and that is TensorFlow keras data sets, the name of the data set is, and then normalization, and then the condition again, xtrain is equal to xtrain by 255, and reshape the input data to have an additional batch dimension. Then you get the xtrain is equal to, this is the again a formula which is to be applied, and this way you can get the this is the pre-processing step for measuring this. Then model definition. In the VAE model, we have an encoder and a decoder that work together. The decoder maps the input image and the latent space using two dense layers with the ReLU of A. A rectified linear unit ReLU is an activation function that introduces the property of non-linearity to a deep learning model and solves the vanishing gradient issue. Activation function. On the other hand, a decoder takes the latent vector as input and reconstructs the original image using two dense layers. Now, input dimension 28 by 28, hidden dimension is 512, and latent dimension is 128. This is the encoder architecture. This again is a code which can be utilized, and it is also specified, or rather explained in terms of a photo, which is presented at the right hand side. So encoder input is TF keras dot input. This one the reader or the learner has to practice, and the more he practices, the more confidence he'll get. So encoder input, if TF is equal to TF keras input shape, and here you have to give the input dimension. Then encoder hidden, that is TF keras layer dense hidden, and then the latent, that is TF keras layers dense latent dimension, encoder hidden, and then encoder again TF keras mode encoder input latent. Then decoder architecture, in a similar way we have to write the code for this also, that is decoder input is equal to TF keras input, shape is equal to latent dimension, then decoder hidden is equal to TF keras layers dense hidden dimension, activation is equal to ReLU decoder input. Decoder output, if TF, that is TensorFlow keras layers dense input dimension, decoder hidden, and decoder TF, that is TensorFlow keras mode decoder input, decoder output. Then VAE architecture, input is equal to TF keras inputs, shape is equal to input dimension, latent encoder inputs, outputs is equal to decoder latent, and VA is equal to TF keras mode input and output. So this is how you can train the data. Then training the data, to train the VAE, we can utilize the Adam optimizer and the binary cross entropy loss function. The training is performed in mini batches where the loss is calculated and gradients are back propagated for each image. Repeat this process. Now this again is a code which one has to write for getting it. So loss function is equal to TF keras losses piracy in binary cross entropy, then optimizer TF keras optimizers dot Adam num epochs, that is number of epochs there or iteration, is equal to 50 for epochs in range. This is the conditional, putting it into a loop. For x in x train, x is equal to x, the TF waxes, and then with TF gradient tape, S tape reconstructed, and then loss, then grads, and these are all fixed kind of codes which one has to write in the editor, and then one can get the output accordingly. Variational at autoencoder, here you will get the output as epochs. First, that is first iteration may give you a loss of minus 0.3559. The second epoch may give you a loss of minus 0.3550. Thank you.